Okay, so in this video, we're going to talk about the special angle in circles. And to start, we're going to define some things. The first thing that we're going to define is what an inscribed angle is. An inscribed angle, basically, if we have a circle, right, we have that circle. And if you remember, an angle has sides. So an angle with sides, we have sides. So let's draw that. We have sides. That is an angle, right? And we have sides that contain the endpoints of an arc. So we have the endpoints of the arc. Let's call this A. Let's call this B. And with the vertex of the angle, remember that an angle has a vertex right there. Let's call it C. Okay. There is a point of the arc other than an endpoint of the arc. So that's basically the definition. We have two sides, right? The vertex is on the arc, right? On the circle, and the endpoints are also on the circles. But obviously, when they intercept the circle, we have an arc. So this is basically an inscribed angle. Okay, so we said that angle ACB intercepts arc AB, basically. Okay. We can also say that angle ACB is inscribed onto an arc. Arc ACB. ACB, right? Is inscribed in this piece of arc. All right. Let's review some things. For example, what if I have maybe I have a circle. Let me erase all this. Maybe I have a circle, right? And the question is, whoops. Right. And the question is, do you think that this is an inscribed angle? Of course, it isn't, because look, the vertex of the angles is outside the circle, right? What if I draw it like this? What if I find the center of the circle, and maybe I draw an angle like this, right? I'm intersecting an arc, right? I have the endpoints of the arc, but again, the vertex is not on the circle; it's in the middle. This is a central angle, so that's a no. My bad. I just erased the circle. All right, let's try another one. What if we have a diameter? What if we have a diameter and we have a tangent line, right? This is on a right angle. But again, we don't even have an endpoint of an arc in this case. Okay, so if you notice, the inscribed angle must be like this always. Okay. Let's do a couple more examples. Maybe we have a circle again. So maybe we have a circle, right? And this is the center of the circle. Well, that's a little bit crooked. Let's put it there. We have a diameter, and maybe we have an angle described like this, right? Described like this. If you notice, this is angle, I don't know, A. Angle A is inscribed in a minor arc, right? What is the minor arc? The minor arc is this, right? This is the minor arc, okay? And we have also a major arc, this big one right here. For the major arc, it's intercepting the major arc, but it's inscribed in the minor arc, all right? So that's how it works. What else? Let's try to draw it a little bit differently. Let's try to draw it maybe like this. Let me erase that thing. Yeah. Whoops. All right. Maybe we have an angle like this. All right. And it's like that. Okay. Let's call this angle B. Okay. Angle B, it's inscribed in the major arc, right? Because you have a major arc here and it's intercepting a minor arc. This is really important. If it was maybe maybe like this, maybe touching the diameter. Maybe I'm not quite precise, but you notice that it's intercepting the diameter. Then it's inscribed in a certain semicircle, and it's also intercepting a semicircle. So this is how intercepting angles and inscribed angles work. Okay, so the next theorem says the measure of an inscribed angle is equal to half the measure of its intercepted arc. So if we have a circle, we have a circle like so, right? And maybe we have an angle that is intercepted, like we have it like this, right? And maybe we have it like that, okay? And we have an intercepted arc right here. Um, it's really easy when we think in central angles, right? We have a central angle. We know that the measure that we have here is basically the same measure that we have on the arc. But in this case, things change a little bit. The only thing that we need to consider is that if we have the measure, precisely the measure of this one right here, of this angle one, then, and let me put names. This is angle 2. And the measurement of angle 2 is going to be equal to the measurement of angle 1, but divided by 2. That is the general idea, right? If we put names to it, maybe we do it like this. Right? Maybe this is A, this is B, this is C, this is P, and that's it. Then the measurement of angle BAC is going to be equal to the measurement of BPC divided by 2. We can rewrite it like angles, right? Or we can write it as arcs, for example. In this case over here, we do not talk about the measurement of the angle 1 that we had here. We talk about the arc. So we said that the arc BC divided by 2 is going to be the same measurement. This is the general idea, and it works for any type of intercepted arc. From that theorem, we have 3 corollaries that are very interesting. The first one says an angle inscribed in a semicircle is a right angle. This one, it's really cool because you have a circle, right? And there's the final semicircle. That is my semicircle. Any inscribed angle that I do here on the semicircle, let's do it just on top, right? If I do it here, right, that will form a right angle. So this is a right angle. If I do it over here, maybe I do it there, right, it's going to be a right angle. Maybe I do it in the middle. If I do it in the middle, that's going to be a right angle. Okay, so that corollary is really cool because it gives you an idea of always having a right triangle and a semicircle if you intersect the diameters. Okay, so what about, let's draw another circle. What about the second corollary? The second corollary said the opposite angles of an inscribed quadrilateral are supplementary. This one is also interesting because if we have, oops, it's more like an oval. All right, this one is better. So maybe we have a quadrilateral like this. I don't know, let's put it like this, right? And what it's saying is that the opposite angles, this angle and this angle, like 1 and 2, right? If I measure, if I add the measurements, the measurement of angle 1 plus the measurement of angle 2 is going to be equal to 180 degrees because that's the definition of supplementary, right? So if this is 80, then I know that this in the front is going to be 100 degrees. Okay. Okay. So corollary 3. It says if 2 angles intersect the same or equal arcs, the angles are equal. So let's suppose again that we have a circle. Again, that's more like an oval. So we have a circle, right? And what it's saying is we have, let's draw a first arc. Let's draw this, for example, this, right? This is our first arc. And maybe we have another intersecting arc, right? And maybe we have another, so we can draw, I don't know, with another color. So maybe we have this, right? we have this, right? We are intercepting the same arc. What it's saying is that the angles, this angle, this angle, this angle, and this angle are all. So if I gave this the name 1, this is 2, and this is 3, then the measurement of angle 1 is equal to the measurement of angle 2 and the measurement of angle 3. When this happens, when you're intersecting the same arc, all right? If you're intersecting the same arc, then it's going to work. You're going to know that the measurement of the angles is the same. And if you know that the measurement of the angle is the same, of course, the arc is going to be the same. Okay. We can define a couple things before talking about the next theorem. And those definitions are a secant ray and a tangent ray. A secant ray, it's basically a ray that lies on a secant line and contains both points of intersection within the circle. That means that if I have a circle, okay, and I have a ray that does this, that is a secant ray. Okay, that's it. That's basically the idea. If I have, well, let's define the other one. It's called a tangent ray. A tangent ray is going to be a ray that lies on a tangent line and contains the point of tangency. So if I have a point of tangency here, that's the point in which the line or the ray touches the circle, and I just draw a ray like that, that is a tangent ray. Okay, so I can draw it like that, or maybe I can draw it like this. It's exactly the same thing. Okay. All right. So with those definitions, we can work on the next theorems. The theorem says the measure of an angle formed by a secant ray and a tangent ray drawn from a point on a circle is equal to half the measure of its intersected arcs. Well, this one is really simple. Again, because we have a circle. Whoops. I don't know. Yes. All right. We got a circle. Let's suppose that our center is here, right? And since it's saying the measure of an angle formed by a secant ray and a tangent ray. So let's define a point of tangency here, right? Let's suppose that we have a tangent ray like that, okay? And we have a secant ray. I don't know. Let's suppose that is our secant ray, okay? Because it's touching 2 points. Okay, what it's saying is, and let's put names to it. Let's call this S, this R, and this T. What it's saying is that the measurement of angle SRT is going to be equal to half the arc RS or SR. So it's going to be half this arc right here. Okay, it's going to be half of that. But what happened if we draw it differently? What if oh, I erased the circle again. What if the ray is not there, the secant ray? Maybe it's there. The secant ray is there, and now we have S here. Well, it's exactly the same thing. SRT is the measurement of the angle, this angle right here. And it's going to be half this arc right here. Okay? SR, my bad. So that is the general idea for this theorem. For the next theorem, we have that the measure of an angle formed by 2 secants that intersect inside the circle is equal to half the sum of the intercepted arcs. All right, so again, we have a circle. Let's draw it. Let's draw a circle. So we have a circle, okay? And we are going to have 2 lines intersecting inside the circle. Let's define the center. So the center is there. And maybe we have that line, right? And maybe we have that line, all right? So the measurement of angle formed by 2 secants, so we have 2 secants that intersect inside, they're intersecting right here, okay? It's equal to the sum, to have the sum of the intercepted arcs. So if this is, let's call this, let me use a different color. This call M, and let's call this N. Let's call this R, and let's call this T. All right. So what it's saying is, and let's call this P, I guess. So what it's saying is that the angle formed by the 2 secants, it could be this one. Let's name it angle 1. The measurement of that angle, the measurement of angle 1, is going to be equal to half the addition of the two arcs. Okay, so if I add the measurement of this piece of arc, that means RT, to the measurement of this piece of arc, MN, the measurement of MN. All right, so that is the idea. You can always find the measurement of this angle if you know the arcs, or if you know the angle and one of the arcs, you can find the other measurement. Okay, so that will help you solve a lot of problems related to measurements with intersections. Okay, let's look at another theorem. Okay, so in this one, we have the measure of an angle formed by two secants that intersects, well, intersecting, this is a little wrong, but still, intersecting outside the circle is equal to half the difference of the intersecting arcs. So what it's saying is we have a circle, right? In this case, we have an angle formed by two secants outside the circle. So we have basically something like this. Two secants intersecting outside the circle, right? Let's call this point of intersection P. Let's call this A. Let's call this D, right? Equals half the difference of the intersecting arcs. So if you notice, we have two different arcs being intersected. So let's call this N and let's call this N, right? So the idea is the angle P is going to be equal to the difference of the measurement of the two arcs divided by 2, right? So half is going to be half the measurement of angle of arc AD minus, since it's a different, the measurement of arc MN. That is the general idea. Okay, so you just basically need to subtract the two. Okay, it's really common that to help you out measuring the arcs, that you draw lines. For example, if you draw a line here, now you know that this angle is basically the same as this, right? Or if you do it like this, right? Now you know that this angle is basically the measurement of this. Okay, so it's really important that you notice how to be able to identify the measurement of the angles. Let's talk about the last theorem. It says the measure of the angle formed by a tangent ray and a secant ray intersecting outside the circle. So let's draw the circle. All right. In this case, we're going to have a tangent ray. So let's suppose that we have a tangent ray like that. Okay, this is the point of tangency. Let's call it, I don't know, B. And a secant ray. So let's draw it like that, right? This is P. All right, so this is A. This is B. No, we already have B, so let's call this Q. All right, so the measure of an angle formed by a tangent ray. This is the tangent ray. Look at it. It's only touching one point, the point of tangency. And a secant ray, we have 2 points intersecting outside the circle at point P, is equal to half the difference of the intersecting arcs. All right, so what we have is that the angle P is going to be equal to half the difference of the arcs. So the measurement of AB, arc AB, minus the measurement of PQ or QB, the measurement of QB, the arc, right? So that's how you can be able to find the measurement of the angle. Again, remember that you can define or draw more lines and be able to compare the values if you want, right? This angle right here, the measurement of this angle is going to be this arc, and well, you can keep drawing things like I can draw a segment here, and the measurement of this is going to be basically this. All right, that arc. I think that wasn't the last theorem. The last theorem is this one. It says the measurement of the angle formed by two tangent rays intersecting outside the circle is half the difference of the intersected arcs. So it's basically the same idea. It's basically the same idea. We have a circle. But in this case, we are thinking on tangents. So we have this tangent, and we have maybe this tangent. Whoops, that's a secant. That tangent. Whoops, it's not okay. we have this tangent, all right, intersecting that point. Okay, so this, let's call this, I don't know, X. Let's call this Y. Okay, so what it's saying is the measurement of the angle formed by two tangent rays intersecting outside the circle is half the difference of the intersected arcs. So we need to define other points to be able to then differentiate the two arcs. So let's call this one M and let's call this one N, right? So angle P is going to be equal to half this arc, the major arc YMX, YMX minus YNX, right? All these measurements, right? Remember that these are measurements. So that's the ideas for all the theorems that are related to special angles inside circles. If I'm able to upload another video before the end of the night, I'll do it with some problems. So you can work on them tomorrow.